Hello everyone, my name is Zaman Shrivastava and I'll be presenting our work CLIP-Lite Information Efficient Visual Representation Learning from Textual Annotations. This work has been accepted at AISTATS 2023 and is a joint work between University of Virginia, Salesforce Research, and Rice University. The motivation behind this work is to extend the capabilities of multimodal contrastive learning methods like CLIP to resource and data constrained settings by looking at vision language contrastive learning from an information theoretic perspective. Current multimodal contrastive methods suffer from the requirement of large number of negative samples for optimization, which is achieved using large batch sizes or memory banks, etc., and also require a large-scale training dataset. For example, CLIP uses 400 million image text pairs for its optimization. In this work, we present an efficient GST-based objective that can be optimized with just one negative sample, and as such, we demonstrate that we can train on much smaller dataset with very small batch sizes as well. As such, we are able to extend the favorable properties of multimodal contrastive methods to low data and low resource settings. Okay, so let's first understand the connection between contrastive learning and mutual information maximization. So it has already been shown that all contrastive frameworks essentially learn by maximizing the mutual information between different views of the same data point. For instance, in the case of images where self-supervised learning is being pursued, it is achieved by maximizing the mutual information between different augmentations of the same image, as done in a famous paper called Sinclair. So overall, for contrastive learning, we need to represent the same data in two views and maximize the mutual information between them. So in our case, where multimodal text and image representation learning is being pursued, we consider that the caption of the image and the image itself encode the same information just in two different types of encoding. So we essentially try to maximize the mutual information between these two modalities for paired images and try to minimize the mutual information for unpaired images. So what is mutual information? So mutual information is just a fundamental quantity that measures the mutual dependence between random variables and can be used to model complex relationships between them. For example, you can see on the animation on the right that the mutual information is able to capture more complex relationships as compared to the covariance. Formally, MI is just a quantity that determines how divergent the joint distribution of a pair of random variables is from the product of their marginal distributions. That is, information between x and y is just defined as the scale divergence between the joint distribution of x and y and the product of their marginal distributions. However, estimating mutual information between high-dimensional random variables is notoriously difficult. Recently, in a paper called Mutual Information Neural Estimation, MINE, a lower bound on mutual information is estimated between high-dimensional variables using a neural network which is trained to distinguish positively and negatively paired samples. Essentially, this neural network is trained to distinguish samples from a joint distribution and a product of marginal distributions. Based on the output of this neural network, a common tractable lower bound on mutual information is then optimized to maximize the mutual information between the high dimensional variables. Two most commonly used lower bounds for this method are the Donsker and Vardar bound and the info-NC bound. Let's talk about the info-NC bound on mutual information a little bit more. So the info-NC bound looks like this, where you can see that the expectation is over k independent samples from the joint distribution. One caveat of this bound is that its performance is directly dependent on the number of negative samples that are used for its optimization. And as we increase k here, you will see that the performance of this bound becomes stronger and stronger. But for smaller values of k, the performance is not very stable. Another caveat is that because of this information inefficiency, the model requires a large batch size or a large memory bank to sample a large number of negatives from for a reasonable optimization performance. Before we move on, let's just quickly review Jensen-Shannon divergence or JSD. Similar to KL divergence, Jensen-Shannon divergence is another way to quantify the difference between two probability distributions. Essentially, it just uses the KL divergence to calculate a normalized score that is symmetrical. This means that the divergence of the distribution P from Q is the same as the divergence of the distribution Q from P. And because of this property, a GSD can also be used as a legitimate distance metric. So overall, the Jensen-Shannon divergence retains the useful properties of KL divergence while being a better distance metric. Now let's get back to our original problem. So we are primarily interested in maximizing the mutual information between two different modalities, and we are not concerned about the precise value of the mutual information which is being estimated. Hence, we use a junction channel divergence based approximation on the expression of the mutual information. So you can see that the mutual information between x and y is equal to the KL divergence between the joint distribution and the product of marginal distributions. We just make a very simple approximation here is that we assume that this quantity is also directly related with the junction channel divergence between the joint distribution and the product of marginal distributions. Once simplified, this expression gives a lower bound, which is based on the junction channel divergence, and this lower bound, interestingly, is insensitive to the number of negative samples and is also monotonically related to the true mutual information, which means that this expression or this objective now can be used as a contrastive objective that can be optimized with just one negative sample and can be used to estimate and then maximize the mutual information between two different random variables. Now, deriving from the Deep Info Max paper, we compare the performance of the JST-based bounds against the Info-NC and the Donsker-Verdun bound. The figure here shows self-supervised classification accuracy achieved by the model using different bounds um, for optimization against the log of the batch size used for training, which is a proxy for the number of negative samples being used. We can clearly see that the performance of the JST bound is insensitive to the batch size, whereas both Info-NC and the Donsker-Verdun bound degrade at lower batch sizes. We also see that towards the end, with a very high batch size, the NC bound is able to outperform both other bounds, but is unstable at lower batch sizes. Okay, so now coming back to our overall CLIP-Lite framework. We first encode the image, its caption, and one negative caption using the image and the text encoders respectively. The text encoder here is shared between the positive and the negative caption. We then project the representations to a shared latent space and compute the alignment between the positive pair and the negative pair using dot products. The alignment score is then passed to the junction channel divergence based objective function we derived to estimate and maximize the mutual information. On the bottom figure, you can see that while CLIP requires unpaired captions from all images in the batch as negative samples, CLIP-Lite can be optimized by just randomly picking one unpaired caption as a negative sample pair. This gives us extreme data efficiency and allows our model to be trained with very small batch sizes and on very small data sets. So here we validate the data efficiency claims of our method. We can see that when CLIP is trained on the COCO dataset with all of the images, which is 118K images, it achieves a 74.2 linear classification accuracy on the Pascal VOC dataset. And note that the backbone here is kept frozen. And it achieves a 33.2% linear classification accuracy on the ImageNet 1K dataset. You can see that the CLIP-Lite method, which is trained on 25% of the COCO captions dataset, which is 29.5K images, already outperforms the CLIP model, which is trained with all of the images on the COCO dataset. Whereas when the CLIP-Lite model is trained on the COCO dataset with 100% of the images, which is 100K images, it grossly outperforms CLIP COCO, which is trained at the same scale. On the bottom, you can see these plots. We show that at any subset of the COCO dataset, the model is able to outperform the CLIP model, which is trained on the 100% of the dataset on both this ImageNet and the Pascal VOC linear classification tasks. We now demonstrate the visual grounding performance of CLIP-Lite on the RefCoCo Plus dataset. We show that the CLIP-Lite is able to localize textual descriptions to relevant areas in the image, shown here through visual GradCam visualizations using the alignment score with the mentioned textual description. Top left shows that CLIP-Lite is able to localize the action phrases such as bending over. This demonstrates the value of learning from semantically rich textual captions, and that the model is able to learn a joint latent space between images and text and is able to connect relevant visual patterns to the corresponding textual descriptions. We now describe other empirical results we observe using our CLIP-Lite model. In Table 5, we evaluate zero-shot transfer performance to the CFAR10 dataset. We observe that CLIP-Lite trained on the COCO dataset is able to outperform a similarly trained CLIP using 3 different prompt templates. We also observe that CLIP-Lite prefers more descriptive prompt templates rather than CLIP. In Table 1, we evaluate linear classification performance on the Pascal VOC dataset and the ImageNet 1K dataset. We can see that in this setting, CLIP-Lite is able to outperform CLIP trained on COCO and is comparable with other more complex methods like Vertex that are trained using image captioning objective. Table 4 also demonstrates the superior text and image retrieval abilities of CLIP-Lite over the visual n-grams baseline and a CLIP model which is trained at the same scale. Finally, thank you so much for your interest in our work. You can find our code publicly available at this repository, and please feel free to email me if you have any questions or need any clarifications. Thank you.